Hello everyone, I am MD Rafil Alam Ratul from Department of Electrical and Electronic Engineering, American International University of Bangladesh. I am pleased to present our work title Shape-Based Interpretable Gradient Boosting for Cross-Hemispheric Renewable Energy Green Score Generalization. This study focuses on predicting renewable energy feasibility across global cities and more importantly explaining the prediction using shape-based interpretable machine learning. Background. Renewable energy planning depends on solar radiation, wind speed, location, and time. These variables interact in nonlinear ways, so conventional approaches may not fully capture their combined effects. Machine learning can learn this pattern, but energy planners also need transparent explanations. Therefore, our work combines predict with explainable AI. Then, a research objective. The study has five objectives: develop a green score prediction framework, compare six models, evaluate performance using R squared and error matrix with five-fold cross validation, identify key drivers using SHAP and test the framework across the 10 cities. The dataset contains 1,920 hourly records and 14 engineered features. Then literature review. The literature review mainly covers solar forecasting, wind forecasting, and composite renewable uh, indicates, and explainable AI. However, these areas are often treated separately. Our study connect them by predicting a composite gain score, comparing multiple models, and using shape to explain the dominant uh, meteorological and temporal drivers. The research gap and contribution. Major gaps remain in single city focus, separate solar or wind prediction, limited algorithm comparison, and weak explainability. We address these gaps through a 10 city cross hemispheric 6 model framework. The contribution is an explainable uh, screening tool that converts model output into planner-friendly evidence. Methodology. The methodology follows a clear pipeline and data injection, quality checking, feature engineering, and model training, evaluation, and shape interpretation. After testing six models, the best model is explained with SHAP. This means the workflow moves from raw hourly data to validate prediction and then to interpretable decision support. Dataset and features. We used the global green energy pulse dataset with 192 hourly records per city, covering 8 days in January 2026. The 10 cities include Beijing, Berlin, Cairo, Lagos, London, Mumbai, New York, Sao Paulo, Sydney, and Tokyo. Features include methodological and geographic and temporal variables. Exploratory data analysis. Um, the EDA shows how solar radiation and wind speed vary over the daily cycle. Solar radiation follows a clear day-night pattern, rising during daylight and falling at night. Wind speed is more irregular because it depends on local methodology and geography. That justifies a machine learning approaches. Result analysis. Um, Among the six models, these tree-based impressibles perform very strongly. Gradient boosting achieved the best overall result with R squared is 0.9984 and MA of 0.0120 and RMAC of 0.025 and the MAPE of 1.93%. This shows strong predictive fit for the structure gain score dataset. And then the green score distribution shows many observations in the moderate range and fewer observations at very low and very high values. This is useful because it confirms that the model learns from different renewable favorability conditions. Future data expansions can further strengthen the prediction at the extremes. Then shape and feature importance. Shape explains which feature influence the model and in what direction. The global shape result shows that wind speed and shortwave solar radiation dominate the prediction. The beamswarp spot shows the higher wind speed and stronger solar radiation generally push the predicted gain score upward. The radar simulation. The simulation visualizes how predicted gain score changes under different resource and time condition. It translates shape-based feature response into an integrate planning view. The figure should be understood as a model-based scenario visualization, not as a long-term climate forecast. Comparison with existing work. Compared with existing studies, our work is bordered in four ways. It uses 10 cities instead of one, predict a composite green score instead of isolated solar or wind output. Benchmarks 6 algorithm and integrate SHAP interpretation directly into the framework. Challenges and future direction. The main limitation is the short January 2026 data window. Future work should be multi-year and multi-season data, include hydro, geothermal storage, grid cost, and policy factor. The test LSTM and transformer models when longer time series data becomes available. Decisions, discussions. The findings shows that tree-based ensembles models are highly suitable for structured renewable energy data. A compact set of interpretable variables, especially wind speed, solar radiation, can estimate the green score very accurately. Shape makes the result more useful and practical planning. And this is our reference. And thank you for your attention. In summary, this study presents an accurate and explainable gradient boosting framework for renewable green score prediction across the 10 global cities. SHAP confirms that wind speed and shortwave solar radiation are the main drivers. I would be happy to answer your questions.